As the executive director of the Big Sky Institute, I'm always looking for research opportunities that link what's going on here in Yellowstone with very large questions that the scientific community is trying to address. Global climate change is probably the most important question facing our generation of scientists, and tree rings end up playing a really key role in the arguments because it's the first time in the history of humanity that we can document that humans are fundamentally changing the nature of the Earth system. In order to document the changes that we are interested in seeing, we hike up to sites at upper tree line, and our concern is that we get a representative sample. Tree line is the boundary at the top of the mountains between the places where trees can grow and the places where trees can't grow. And it's governed by temperature. What it looks like if you were hiking up there is an actual line on the landscape where trees can no longer grow. And initially, we simply survey what's up there.
And look at this.
Is it drought? It is drought. It's not winter killing.
When we look for tree line sites, we always try to make sure that they're just recording climate. So we go far away from any place that's ever had grazing, logging, or the other ways in which humans alter forests.
This looks like a good place to stop. Let's get organized here a little bit. Let's see. Andy, do you want to go check out the weather station? And Steve, you've got the GPS, right? Why don't you start mapping in some of the deadwood locations? And I'm going to find one of the bigger individuals and start the coring process.
When we first discovered the Grass Mountain site, which is just a spectacular site for doing research, one of the first things we did was put a weather station up there so we could quantitatively understand the growing season environment, and as long as the bears don't eat up the wires, we have the ability to record temperature, rainfall, relative humidity, wind speed and direction for the entire growing season as well as through the winter. So when we get to a given site, it's critical that we core the living trees, and that tells us about growth patterns over the last couple of centuries, as well as coring these dead pieces of remnant wood, which we can then date to be able to understand when there were old upright trees on the landscape in times previous. One of the challenges is to try to actually associate these dead pieces of wood with an actual calendar year date. And it turns out I'm actually one of a handful of people around the world that's had formal training as a dendrochronologist. I study trees, dendro, through time, chronology.
Okay, let's see. Oh, sure enough, here it comes.
We are able to match up the outermost rings of the dead wood with the innermost rings of the living wood, and thereby establish the dates of the dead wood, so we know when it was that that dead piece of wood was actually a tree that was established on the landscape, and probably equally importantly, when it died. One of the goals of our lab group is to be able to not just describe when all these changes take place, but exactly where.
Oh, that's a nice piece there.
We are able to uncover evidence of tree line fluctuating over time. We know that over hundreds and thousands of years, tree lines moves up and then retreats. These broad fluctuations we see in tree line, the moving up slope and then retreating back down slope, is driven in the end by climate. It's the length of the growing season and the warmth of the growing season that allows trees to establish above their current limits, and when conditions change towards colder conditions, it causes the trees to die and retreat back down slope.
I'm thinking these are medieval warm period trees. This is going to be a great site.
When we get out of the field, we head to the lab, and there we have a good long winter's bit of work. We have a large number of samples that need to be processed, and we like to have lots of samples because that ensures that we've got enough data to really make a strong argument that what we're seeing here is climate variability and not some other factor. So when we get to the lab, We mount the cores in such a way that we can see the cells. The cells are facing upright towards the microscope's plane, and finally give them a sand that the best furniture maker would be jealous of. We sand it so smooth that we can see every cell very, very distinctly. We go after very accurate measurements of the rings because it's the year-to-year variability in ring width that's the signal we're trying to detect. For the kinds of trees that we're sampling at upper tree line, where temperature is such an important limiting factor, we have the ability to interpret the variation in ring width that we see in these cores. A narrow ring occurs when temperatures are very cold, the growing season is very short. On the contrary, a wide ring occurs when there's been a warm growing season that's very long. So the sequence of narrow rings and wide rings tells us about the sequencing of cold and then warm years. Well, it turns out in the last couple of decades, we're seeing some truly strange patterns. Temperatures in the last couple of decades are warmer than what we've seen over the last 1,000 years, which is a truly significant finding. We know that this is unprecedented because we've got the ability to push these records back in time, and we have every reason to believe that this is in fact due to human activity. There's upper treeline environments spread all over the globe. So we do this in my lab, we do this in labs around North America, we do this in labs all over the world. And interestingly enough, the kind of patterns we're seeing here in the Yellowstone area are echoed worldwide. So all of these data are not just of interest to a small band of people that think the past is cool for some reason, but they're actually entering into a national debate about the nature of climate change and what we should do about it.